So I think first thing I want to talk about is picking a test date here, right? So we'd finished the chapter 6, lectures or whatever on last class. My thoughts would be, we'll use today as a review day. We'll do 7-1 on Friday, and then our lone class day next week. On Tuesday, we'll take the test, because the other 2 days are asynchronous because of conferences. Thursday and Friday are asynchronous days. Does that gives you an extra weekend to kind of get your house in order, and rather than trying to cram this down our throats this week? Feel good there? Okay. I like that. I think that works as well also. So if you haven't looked at the review, the test format is here on the review in the content library. So we have 3 questions from the chapter 5 leftovers. So that was using those trig, those inverse trig functions as our U substitution problem, and or polynomial division, right? We did that the first day or whatever. There was the bonus content, right? We did that. So you have 3 of those guys. 2 questions about areas between 2 curves. 3 questions of volumes of revolution. 1 work story problem. 2 average value function problems. And the format for questions is going to be similar on the test as here. So like, set up the definite integral and then use your calculator to compute the area. No work needed to do the integration, right? So like, I'm trying in places here to find ways to save you time on the test, where we're going to worry about the setup part. Can you get things set up and then punch in your calculator to get your answer? So like, all of these problems here are just set them up and plug it in. Hi, Luke.
Good morning.
Good morning. Paul, it's for you. And then the, like a work problem, I'd expect maybe we do the calculus here. These average value things do the calculus there, but, and then here again, you're doing the calculus showing your work, but I'm trying to find places where we can just shave off having to do all of that for all the problems. You know what I mean? Especially since most of these, the setup is the troublesome part, and after that it's usually fairly clear what to do integration wise, but just let's save the time. So that's kind of the test format. So if we add those up, what's that, 11 questions or something? So I think that's probably pretty doable. Gives you 8-9 minutes per question. Feels okay. You guys feel okay with the format? And again, the test will look fairly similar to what the review looks like. And I'll get a key in there for the review later today. I just need to get my key scanned. It's written, so I can get that up there for you guys also. But I think with the test not coming till next week, we can touch base again on Friday with questions on stuff. Does that everybody feel okay with the plan, the format, reasonable? I'm trying, Do you guys want to do some questions on homeworks or review stuff, any of that? Let's do that for a bit, and I want to talk about the quizzes you guys took yesterday and what we're going to do with those. It's fine. Nobody panic. It's fine. Blake.
On number 6.5, do you mind doing number 9C? So it's just graphic. I just want to know what they want.
Oh, sure.
Okay, sure.
Can we do just all of these?
Yeah, no problem. I don't mind. Let's do that and just drop in a bunch of these questions. So 9 through 12, the directions ask us to find the average value of f on the given interval. So to do that, you're just going to do like f of pi minus f of 0 divided by pi minus 0, just kind of like a slope, right? You just evaluate the endpoints and then divide by the interval. So Mackenzie, what's sine of pi? Oh, are we supposed to be doing that? Maybe we're supposed to be doing that. Yeah, you're right. Let's do that. Sure. So f_av 1 over pi minus 0, integrate from 0 to pi of 2 sine x minus sine 2x dx, right? So we'll do that. Okay. So I have 1 over pi out front. And what's the antiderivative of 2 sine? What's up? Antiderivative of sine is cosine, so that's 2 cosine. Now to do the antiderivative of sine 2x, what are we going to have to use? Use substitution. Excellent. Oops. Is it negative cosine? Yes. Okay. Mackenzie. That's okay. I'm not mad. I'm just glad somebody caught it for us. Thank you. Okay. So what is the antiderivative of sine u du? Going to be negative cosine u. Everybody agree? So I'm going to have negative of a negative is plus now, right? Because it's subtracting. I have the 1/2 from the du. And then u is 2x. Is that okay with everybody? If we chain that out, we get negative sine 2x, right? You just check it by taking the derivative of 1/2 cosine 2x. You get negative sine 2x using a chain rule, right? You're looking at me like I just grew ahead. So if I want to check to make sure I've done that antiderivative correctly, I can differentiate this, right? To differentiate that, I would use the chain rule. So I'd have 1/2 negative sine 2x times 2, which is negative sine 2x, which is what I have above. So I know I've done the integral correctly, right? Does that feel okay? Mackenzie, are we still doing
Yeah.
You still with me?
Mhm.
Okay. All right. Let's continue on. So if we evaluate now, cosine of pi is -1. So -2 times -1 is just 2. Well, let's write it in so it's a little bit easier if you're going back to look at it. If I plug pi in, cosine of 2 pi is +1. And then cosine of 0 is 1. And cosine of 0 is 1. So let's see, what do we have now? 1 over pi, and we have 2 plus 1/2 plus 2 minus 1/2. So we get 4 over pi. Does that look right to you guys? Okay. So that's part A. Part B, it says we want to find some value C such that the average is equal to f of C. First things first, does such a C exist? Yes, very good. Why? Because that is continuous over the interval from 0 to pi, right? Sine is a continuous function. Sine 2x is a continuous function. Continuous plus continuous is continuous, right? So I'm guaranteed to have such a value. To find that value, I'm going to just plug in that's the function. And woof, how am I supposed to do this algebraically? I don't think you are. I don't think they'd expect you to do that algebraically. I'm not sure how you would do that algebraically. I don't have the foggiest, in fact, how to do that algebraically.
You could just do it like, you just graph it.
Yeah, that's what I would do. Yeah, I would just use my calculator to do that, graph this and find the intersection. Yep. Got to change my mode. We're in doing parametrics in pre-calculus, so I would just do 2 sine x minus 2, or sine 2x, and then I'll do 4 over pi. And I'm going to just graph this from 0 to pi. And I don't know, I'll go by pi over 4s or something. And let's just take a look. I can always adjust the y if I need to get a better picture. Okay, maybe I will. Let's make the y min 0, since it seems like it's always positive there. And then maybe make that 5. That'll give me a little better looking drawing. Okay, so intersect command, first curve, second curve, and then the guess I do have to be careful about because there's multiple places. So one of them is 1.238. And the other one is, oops, daisy. First curve, second curve, and then the guess I do have to be careful about, and I want to move it close to that intersection, so I'm making sure it finds it. 2.808. And then for part C, it asks me to sketch a graph with the rectangle. And the graph that I'm drawing is ostensibly what's on my calculator here, right? Where this is the rectangle. Since I just graphed it over the interval, it's just basically the picture on my graph.
What? What is the what do you mean by the rectangle?
Well, the rectangle is the rectangle that has the same area as the area under the curve. So you have whatever this is. And then my rectangle is just that, right?
Okay.
Where this is 0, this is pi, and this is like 4 over pi or whatever is the height. Well, this is if I look at the picture, this is the line, 4 over pi, right? So the rectangle's height is 4 over pi. You know what I'm saying? So what's the area under that curve got to be? Just 4, right? Because the base of the rectangle's pi, the height is pi or 4 over pi, so the area under the curve is 4. Does that feel okay, Mackenzie? Blake, is that's what you needed? Okay. Who's next? Happy to do some more? Homeworks, review, whatever. Mia?
Oh, could you do one of the work, all that stuff?
Sure.
I don't care if it's like a homework or
Which one do you want to do? Mackenzie, did you have opinion? The review one? Sure. We can do that. Let me do that, and I'll just grab it. All right. So we have a rectangular prism for an aquarium because we're given like length, width, and depth. And we want to pump out 3/4 of the water. Use the fact that the density of the water is yada 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 and gravity is yada yada yada. Okay. So I'm going to be using. Go back to my work notes, and I'm going to basically be using this example kind of as my primer. Now, there's one very important difference between this problem and the problem that I'm about to do. The shape. And that shape actually makes a very big difference. It makes the problem we're about to do much easier than this one. Why?
Because as the water level changes, the rectangle basically stays the same, whereas the cone is.
Yes, exactly right. That's 100%. So notice as the water descends the cone, the circle that's at the top of the water level changes at each height, right? For a rectangular fish tank or whatever, aquarium, that shape of the rectangle at the top of the water, constant, which makes this much easier to deal with because we don't have to do any of this similar triangle mumbo jumbo. And there's really only one thing changing, and it's the distance of the water being pumped out, right? the amount of water not changing, right? Is everybody okay with that? So that's actually very nice for me. Let's go back to this. All right. Grab this thing real quick. All right. So I would start by drawing myself a little picture of my aquarium. And this is 4.75, and this is 3.5. So at some arbitrary height, the volume of water we're moving is going to be like that little tiny skinny little rectangle. Well, it's actually a rectangular prism, but its height is, you know, like this distance is like dx, right? Boy, I wrote that too small for anybody to see anything. All right, so my slice of water here is going to be 6.25 by 4.75 by dx. So what I need to do is figure out how much that's going to weigh. So 6.25 times 4.75 times dx is going to be 29.6875 cubic meters. Remember, the dx is like dx meters, like it contributes to a unit because that's the depth of it, or the thickness of that rectangle. And then I'm going to convert that into kilograms using the density. So I multiply that by 1,000. And I get 229,687.5 kilograms. I'll write that. Oops. Is everybody okay with that? So the force then is going to just be mass times gravity. So that's 29,687.5 times 9.8. So that's 290,937.5. Okay, so far so good. All right. So that's what I need. So work is going to be the integral of force times distance. The question is, what do I want for my bounds then?
So if we're pumping 3/4 of the water out, would we start at like, if it's full, then when we start at a position of, wait, but if we're pumping water out, wouldn't we want a negative integral? So,
Well, I would just consider the tank full to be zero distance.
okay.
So
And then
I would start at 0.
tank empty would be like, what's 3/4 of 3.5?
So you think 3/4 of
Of
3.5? Yeah.
Is that?
Would find the work needed to pump 3/4.
So yeah, the find the word. Yes, that's where the 3/4 is coming from. Is the problem? So 2.625 is what you guys think. Okay. Let's see. So I'm just going to use the calculator to do this because, quite frankly, oh boy, the numbers are kind of gross, right? And the calculus piece is pretty trivial. So we have what, 1,02,370 joules. And I'm not sure on that. Let me look at something real quick. Before we get going, because I'm a little bit nervous about that. No, that should be okay. That's right. Yeah, I think that's right. What was that?
Is that the right answer?
Yes. That looks good. Much easier than the cone one, right? That cone one was kind of nasty. Because two things were changing, right? The amount of water and then also the distance traveled makes it a rough one.
We have a cone.
Do you think if I was going to give you something super complicated, I would have put something super complicated for you on the review also?
I mean, it's like a little thing out.
That's you. I mean, like, honestly, like, you've taken a bunch of tests from me, and I'm like, am I a like curveball teacher?
No.
I try really not to be, right? I try really hard to just tell you what you need to do, and then that's what we're going to need to do, and not mess around with it, right? Like, okay. I just want to. If that's not the case, I would like to know that, but because that's what I was trying to do, was just make it be very straight ahead. Mia, does that Of course. Okay. Mackenzie?
Can we do like one of the first three?
Sure. Do you have a preference, or does anyone have a preference? It sounds like you're up for whatever.
Are they all like the same?
No.
The same process, I guess?
No. Two of them would be, I would be using like trig substitutions, and two of them I would be one of them I'd be using polynomial division.
So can we do one of each?
I mean, sure. All right, let's grab this also real quick. All right, so first thing we're going to ask is we need to identify what to do for the problem, right? Because if you can't look at it and know what to do, you're going to waste a bunch of time mucking around with something. All right. So these are your antiderivative rules that you could use. Let's do 1 and 2, just for the sake of doing something. Take a look at the antiderivative rules here. What can I use on number 1? Zoom into the rules or to the...
Just like, yeah.
Okay, let me just make them bigger. How's that? Sure. Pack your glasses. Let's sit in the back of the class. There's really only one feasible choice here. The tan inverse one. Good. Why did you come up with that as the only feasible choice? Because you have 1 over a polynomial, right? And we can suck that 10 out front and make it 1 over a polynomial. Now the problem is this polynomial does not look like x squared plus 1. So we're going to have to do some work to get it as something squared plus 1. Does everybody feel okay as to how we identified what to do on that one? All right. So let's take the 10 out. X. So let's start by doing that. And now somehow I need to take this and make it look like some u squared plus 1, right? I don't want to write x squared there because I already have x's in the problem and it feels like it's going to get confusing. So how do I take something that's quadratic and make it look like u squared plus 1? Not polynomial division. Completing the square. Okay? Now, we could do this the textbook way, or we could cheat to try to make it easy. Which one do you want to do? Let's cheat and try to make it easy, right? what do I know about when I complete the square for 4x squared plus 12x plus 10? At the end, it has to look something like this, right? If I'm going to be able to do this problem, it must end up looking like that. Everybody agree? So I'm going to use that to say, okay, well, I'm going to do that. And then I remember that the perfect square factoring pattern looks like this. That's an algebra 1-2 thing. So here, 4x squared should be my a squared. So what should a be? 2x, right? Is that clear to everybody? And b squared is 9, so what should b be? 3. And if I do 2 times 2x times 3, do I get 12x? Yes. So there's my perfect square factoring. Boy, was that massively easier than doing completing the square? Yeah, I think so. The completing the square gets messy, especially if there's a leading coefficient. Like it just yucksville. That's a super easy approach if you're like, hey, it's got to fit in this puzzle piece. Let's just like cram it in there, kind of thing. All right. So we have then 10 times the integral of 1 over 2x plus 3 squared plus 1 dx. So my u in this case is going to be 2x plus 3. Excellent. So my du is going to be 2 dx. So dx is just du over 2. Is that okay? So I'll go ahead and make the substitution. Mackenzie, you still happy? Okay. And I'm just going to do this. Just reduce right now with the 1/2 on the 10. So do our antiderivative. What's the antiderivative of 1 over u squared plus 1? Tan inverse of u. But let's not write u, right? Let's just save ourselves a step. We'll write the 2x plus 3. Is that it? Am I done? Very good. Plus c. Why do you need the plus c? It's indefinite integral. Exactly right. Yep. I knew what you meant. It's close enough. Does that feel okay? All right. Let's go back up here and look at number 2 now. Does number 2 fit the form of anything up here? Nope. Good. So what are we going to do? Polynomial division. So I want to rewrite that as polynomial plus remainder over divisor, right? And since this is a degree 1 polynomial, the divisor, Any remainder will be a constant. So I know that when I'm done with that polynomial division, I have something that I can use the natural log antiderivative rule on. Everybody's okay with that? So let's do 2. So we'll start by just doing the polynomial division. What's crummy about this is I have to do it long division wise. Why can't I do synthetic division here? The leading coefficient on the divisor is not 1. Now you could cheat and like factor a 0.5 or a 2 off and like kind of cram it in, but it's like kind of tough to like put it back together again to get what you want. But it's possible to do synthetic division since it is still degree 1. It just like, I don't think it's any easier than just doing the long division.
If you didn't recognize that you could do
Polynomial division always works. Yes, that's correct, Mackenzie. Good point. Synthetic division is the special case that only works for degree 1 divisors. Polynomial division works for everything. All right. How does this start? I'm going to find what times 2x gives me 2x cubed? X squared. What do I do with it then? I multiply that. Okay. When I subtract down, 2x cubed minus 2x cubed is 7x squared minus a negative x squared, 8x squared. Then bring the next piece down. Caution, making sure you distribute the negative sign when you're subtracting down is the number 1 mistake that students make when doing polynomial division. Be careful about that, right? You should remember making that mistake from Algebra 2, but I want to remind you that it's a common one. Okay, next up I ask what times 2x gives me 8x squared, 4x.
It's plus 4x.
Yep, because it needs to match sign-wise, because we're going to just be subtracting. Okay, when I subtract down, what do I get? Good. And then we'll bring the minus 9 down. And then the last number I need up here is plus 1. So I subtract down and my remainder is -8. Excellent. So what I can say here is 2x cubed plus 7x squared minus 2x minus 9 divided by 2x minus 1 is equal to the quotient of that division plus the remainder over the divisor. And it's that substitution that we're going to use to be able to do this integral. So far, so good. From here, the integration should be relatively straightforward, right? I will distribute my integral, so I'll just integrate the polynomial piece, separately, and then I'll integrate that fraction piece separately. Integrating the polynomial is easy though, right? Everybody feel good on that? That's integration like 101 there. You guys did pretty darn well on that last time. Should be able to handle something like that pretty quickly and easily. What are we going to do with that second piece now? Well, I would start by taking the constant out. And we have to make a u substitution here. So we still have that same stuff. One over u times du over 2. And then we can use our natural log. So that's going to be the natural log of the absolute value. Oh, let's do this here. Should just do that there. Make that 4. Of u, but I'm not going to write u. I'm going to write the value, the substitute with the substitution, just save myself a step. What's up? Why is it the natural log? So I just used that antiderivative rule, right? Everybody's cool? Okay. Go back to my stuff here. All right, so I'm all done, right? Plus c, very good. Is that all right? Go back and look at number 3 real quick and just let's pick out what we're going to need to use. Sine inverse, great. Yep. See, because you see the square root of the polynomial in the denominator.
Would you similarly complete the square?
Exactly the same idea.
Same, like you use the same
Trick.
Same trick.
I would do the same trick. Yep.
Yeah.
Yep. Exactly right. Since I know what it's got to look like at the end, it allows me to just use my perfect square factoring to kind of get there, which I'd much prefer that over trying to complete the square on that. When I was doing these, I'm like, why haven't I been doing this the whole time? This is much easier. When I did some practice ones for you guys, when I was writing these out, I'm like, this makes life so much easier. Who's next? Mackenzie, you feel okay?
Yeah.
Yeah, of course. All right. So what I want to do now, I want to kind of talk about these homework quizzes that you guys took for me. I'm not going to count these. I mean, some of them were fine, but some of them were, like, yeah. It was just clear that, like, we didn't know what to do. Like, we gave away points because we didn't understand how things were going to be scored. So let's just use this as like a learning opportunity where we can kind of talk about like how to unpack something, because that's half of the problem was I think we read these and we're just like, I just don't know what to do with this, and I can't unpack it. To figure out what to do, I'll get you a copy. Which ones? You guys had. You have the top. And then what was the second one that you guys had? Maybe like I don't have an extra copy of it. Blake, I lied. I don't have an extra copy of it, but I did.
Is it up on OneNote?
I did put them into the OneNote here, so figure that's probably close enough.
Yeah. Yeah, I just wanted to. I want to like take a look at it.
Yeah, absolutely.
I heard from people it was quite the doozy. Quite the doozy.
Yeah. So, all right. So let's go through this kind of together, right? And I'll talk about, as I read the scoring report and the scoring guidelines on how that the AP published for like how they're instructed to score this problem. We'll talk about kind of what you needed to, where there are easy points to pick up and where there's easy points to lose. So one thing straight away, part of the reason I didn't want to count this is I made a goof and mislabeled the ones that you're supposed to use the calculator on, the one that you weren't supposed to use the calculator on. Yeah.
Wait, were they confused switched?
Yeah, the top is a no calculator problem. And the other one is the calculator one, like a bonehead. So you can, yeah, I cool-licked it. And I did for both classes too. So, way to go. Okay, let's walk through this though, kind of nicely and slowly. Okay. So it says that we have a company designs spinning toys using the family of functions y equals c of x, or cx square root 4 minus x squared, where c is a positive constant. The figure above shows the region in the first quadrant bounded by the x-axis in the graph. Each spinning toy is of the shape of a solid generated when such a region is revolved about the x-axis. Both x and y are measured in inches. Okay? So what is this thing going to look like when they make it? Like a top. Yeah, like a radish, like a top. Like a little stupid toy you had when you were a child, right? So the first part A says find the region or area of the region in the first quadrant bounded by the x-axis and the graph of y equals cx square root 4 minus x squared for c equals 6. So just looking for this area, right? That's it. Integration 101. So how do we write this? Okay, where'd you get the 2 from, though? So we're going to have the integral of 6x square root 4 minus x squared dx, right?
Yeah.
We know that much. So yeah, we need, obviously this point is 0, but we need to figure out what that x is, right? Because that's going to be our other bound. So to do that, I'm just going to plug 0 in for y, since I know any point on the y-axis has a y, or any point on the x-axis has a y-coordinate of 0. How do I solve this? Without a calculator. What was that? Yeah, you can use the zero product property, so I can take the cx and set that equal to 0, and the root 4x squared, or square root 4x, or 4 minus x squared equal to 0. Now, c is positive, so I can divide both sides by c. Well, yeah, I knew 0 was one of the intercepts. What am I going to do to solve this other one? Square both sides. Excellent. Now what? Subtract 4 from both sides. Good. Well, you can't square root yet. Yeah, divide by negative or whatever. Square root both sides. When we square root both sides of an equation, we get a plus or minus. But we're in the first quadrant, so we throw out the minus. Writing this down was 1 point. That would have been 1 point, having that there. Next step, what do we need to do? We need to integrate this now. To integrate this, what do we need to use? U sub, great. What's my u going to be? 4 minus x squared. So du is negative 2x dx. So we need du to be du over negative 2 is equal to x dx. Does that feel okay? So 0 to 2 square root u times, oh, we still have that 6 there, du over negative 2. Now, what else could we have done here? And what else probably should we do here? Yeah, let's adjust our bounds. And then let's do this. Let's put that out there. You guys cool with that? Okay, how do I do the antiderivative of square root x? Antiderivative of square root u. Everybody's good? This is 1 point, getting to there. The final point then for this problem would be evaluating Mackenzie.
So because you 0 and 2, you don't sub u back in.
Correct.
Okay.
You could also have left the bounds of integration alone and then subbed the x's back in.
So if you don't, sub the u back in, you leave the bounds, but if you, up, no.
Other way around.
I got it.
Yeah. And either way of doing it is fine. You'll get the same answer either way.
Okay, thank you.
I think it's usually easier to change the bounds and leave the u for a definite integral problem. But indefinite, you always have to put the u back. So how do you do the 4 to the 3 over 2? No calculator.
Square root or over 16.
I would do the divide by, or the over 2 is the square root. Let's do that part first. Square root of 4 is 2, and then 2 cubed is 8. 2 times 8 is 16. So I have 16 over 3 times 3. And the negatives will cancel out, so I just have just 16. That's the third point for that problem.
Can you go back up to the problem? I want to see like the language of it, because that's. That was all for A, correct?
Correct.
How long do you get on these problems in the test?
I'd have to double check. So you have, let me look here. I think I have it on here somewhere.
Like north or south? 5 minutes.
North.
Okay.
So I don't have the time breakdowns here, huh? I'll have to look it up. The free response is broken up 4 and 2, so there's 4 calculator ones, 2 no calculator ones.
Okay.
And I think it's in the neighborhood of, you get like about 10 to 15 minutes for one of these problems.
Okay.
Is it always an ABC?
Is
Is it always 3 parts of one?
No, there might not be.
Oh, okay.
There's always 9 total points for a free response question,
Oh,
but how those 9 points are divvied up, there could be 4 parts, and there could be like 2, 2, and 1.
Are they
or something.
usually non-reliant on each other, or was that just a?
No, they are.
test?
They're almost always not
Oh,
reliant on one another, where if you can't do one part, you still might be able to do the other 2 parts. And that was the case for all of these problems that I chose. None of them relied on the previous part. All right. So let's do part B now. I think I have this all separated, so I can just grab this. Yeah. Oop. Do that. All right. So part B says it is known that for y equals cx square root 4 minus x squared, its derivative is equal to that stuff. For a particular toy, the radius of the cross-sectional circular slice, is 1.2 inches. What is the value of C for this toy? So what is the 1.2 telling us? That's a y for here, right? Because if I go back to my picture, we're talking about like this slice, right? Everybody's okay with that? What would I call this point on this function? That is a maximum. What do I know about the value of a derivative at a maximum? It is 0. So noticing that dy dx is equal to 0, that's 1 point. That's all you needed to do, was just make that observation and write it down. and that was a point. Okay, to solve this equation then with no calculator, what do I do? Correct. So a fraction is equal to 0 only when the numerator is equal to 0. So I can just ignore the denominator. It does not matter. Everybody's cool there? How do I solve this then? You could split it, but do you even need to split it? What do we know about C? It's positive, so is C equal to 0? No. So guess what I can just do? Divide it to both sides and it's gone, right? Don't even need to worry about it. I saw some of us say C could equal 0 or this result, but it's no, we're solving for C. C is positive. It was declared so in the problem. Okay, how do I solve this then? Yep. Then what? Divide by -2. And then what? Square root both sides. And then what? Discard the negative. Good. Now that I have this, and I know that y is equal to 1.2, I just plug these back into this equation. And solve for C. What's square root of 2 squared? 2. 4 minus 2 is? So that's square root of 2 times 2 is? Square root of 2 times square root of 2 is? 2. That's the second point for this problem. That was it for part B. We found the value for C. Okay. Last one. So how many points have been covered so far? 5. How many left have to be in this problem? 4 more points. All have to be here. Okay. So it says for another spinning toy, the volume is 2 pi cubic inches. What is the value for C of this toy? So the volume is equal, how do I calculate the volume of one of these toys? The integral of, what are we using? Discs, washers, something else? Disk, good, so it's pi r squared, and the r in this case is? Okay, and then dx. That's 1 point, just noticing that this was discs and getting it in the correct form. Okay, what are the bounds of integration? 0 to 2. That was 1 point for getting the bounds correct and making sure the pi is on there, whatever. Okay. Let's go ahead and do our antiderivative then. Well, actually, let's integrate this. What am I going to have to do to integrate this? I'm not going to do either of those two things that you just mentioned. I'm going to clear that exponent. How do I square cx square root 4 minus x squared? You square the c, square the x, and then you square the square root. Everybody okay there? And what wonderful thing has happened now? Well, I can now pull the c out, right? Or the c squared out. And then I can just distribute the x squared through. And that's now a piece of cake, right? One point for getting the antiderivative, correct. And the last point is just going to be solving for c. So 2 pi. And then if I plug the 2 in, I have 32 over 3 minus 32 over 5. And then I guess minus 0 if you want. So I can cancel the pi's. What's 32 over 3 minus 32 over 5?
Is this the no calculator or the calculator?
No calculator. Multiply this by 5 over 5, so that's 160 over 15. Minus multiply this one by 3 over 3, 96 over 15. What do we get there? 64. Oof. Over 15. So I multiply both sides by the reciprocal, and I get 30 over 64 is equal to c squared, but I can reduce that to 15 over 32. And then we just square root both sides. And what can I do with this? Discard the negative. That's my final point. Do I care that there's a radical in the denominator? We do not. On a no calculator problem, don't pretty your answer up. Once you got an answer, just leave it. They will not penalize you for an unsimplified answer. How'd that go? It seemed you guys made more progress on this one because you definitely spent more time on this one than the second one. But that once you've seen it gone through, it's like, okay, this is maybe not so bad. All right. Let's look at this next one here. I don't think I broke this one up into parts where I can reshuffle the lettering, so I'm going to have to label it. Let R be the region in the first quadrant bounded by the x-axis in the graphs of y equals natural log x and y equals 5 minus x, as shown in the figure above. Find the area of R. Okay, so you want this region in here, correct? Okay, how are we going to do that? Okay, we need to know where the intersection is. Great. How are we going to find that point of intersection? With our calculator, because this should have been the calculator one, not the other one. Mr. Kulik, you boogered that thing. It's my fault. I picked out my problems and then I collected a bunch of them and I must have mislabeled my stacks. I'll just do Zoom standard to look at that. Okay. There's my 2. Intersect command. Enter, enter, enter. Enter, enter, enter. And I have 369, 131. Okay? Great. Now that we have this, what can we do? Okay. So what are we going to do then? Mm-hmm. Mm-hmm.
3.69 to 5 minus x.
Okay, that would be 1 point. And that stuff was 1 point. Guess what the final point's going to be? The answer. How are we going to get that answer? Just type into the calculator, right? I'm going to skip doing that because we're running short on time here. Is everybody okay with that? How else could you have set this up, though? Because this is not the way I would have set it up. Oh boy. So I would do it, I would integrate with respect to y. Because then I only need one integral. It's fine to do what you did above. So it would be this one minus this one, right? But I have to write that in terms of y. So I would have like, what's that going to be? That's going to be 5 minus y is equal to x. And this one is going to be e to the y is equal to x. So the furthest right one is the 5 minus y minus e to the y. That's the other way you could have set it up. That's the way I would have done it because it seems easier to me. But didn't have to. Oh, I guess we're out of time, aren't we, here? Remind me again that we need to finish going through this next time. And we'll do some more of this on Friday before we do 7-1. And again, if you look through your stuff and you have more Chapter 6 questions, we can handle some of that on Friday also. You guys feel okay?